So that's one idea, but you don't actually need to know the derivative. We'll come back to exactly how you approximate a function when you know the function at different points, right? But the general idea here is that for each interval, you're going to know the function at more and more points. You're going to look for more and more functions, for more and more points at which to evaluate the function. Then you're going to give the answer for say a quadratic function that goes through all of these points. So what you're effectively doing is approximating the function as a locally quadratic function. Another way of saying that is that you're ignoring the higher order terms. And again, with the Taylor expansion, you can expand the derivative in terms of so two things to keep in mind for the future, because just going into that right now would be too technical, too unclear. So when we talk about differentiation, all right, we can approximate f prime at a in terms of f at a and f at b, or x minus a. Sorry, at x. So given multiple values for this function, we can approximate the derivative and use that to get the formula that we need, and then it's just plug into this general structure, right? And you're done, or at least it's going to work. Another thing is interpolation, right? It's just given f of x1, f of x2, f of x3, you can find a parabola. So you know, something like 3x squared minus x plus 5, for instance. That's what I mean, quadratic function that goes through all these points, right? So by differentiation, if you just look at the first, say, 3 terms in this expansion, in this Taylor expansion, you're going to get a polynomial of degree 2. By interpolation, you can also get a polynomial of degree 2 by only looking at 3 points for the function. If these two polynomials agree on at least 3 points, even though you came to their final form by different methods, it's going to be the same they're going to be exactly equal, because you can't have two parabolas which are equal on three distinct points and yet are not equal everywhere. And if you're equal everywhere, your formula is going to be the same when you write it in this form, you know, constant x squared, constant x, constant. The reason for that is that these constants are the only thing that change. You only have three constants, so well, I mean, there might be more elaborate arguments for that, but essentially, once you decide what the value is at three different points, you're committed in a sense. All right. So let's open it to questions. See if there are any questions. Probably aren't any questions. If you do have a question, feel free to type it in. Okay, so once you've got your formula like this, there are things you can do to make it a better, you know, to make it work better. If you notice in this case, you will see that we compute f at a given point. Say f at, you know, this thing, f when I is equal to 1, right? This thing would be when I is equal to 1, it's the same, but with I equals to 2. There's this expression, right? F of A plus, you know, some variable times H. And basically written like that. See if we call that G. G at this thing is equal to that. Then what we see here is basically G at I plus G at I plus 1. But since we're sweeping over I, when I is equal to 0, we have G at 0 and G at 1. But when I is equal to 1, we have G at 1 and G at 2. So we compute G at 1 2 times, and we add it, you know, we add 1/2 times h the first time and 1/2 times h the second time. And we do this for almost every point, right? The only points where we don't do this is the first point, where we only add it once, and the last point, where we only add it once. So we could rewrite this. You know, we have this sum, and because we can reason about the value of this thing, we can change the code so that we get the same result, but we compute f less often. So, okay, one kind of ugly way would be if I is the first, or I is equal to n. Then we add g of I over 2. Else we add g of I not over 2. So what this basically says is the first and the last, you just add them once, and so you get 1 over 2, or h over 2, but every other you add them twice, so you get 2 over 2, which is 1. Okay, so that's one thing you can do. It's by no means the most pretty thing you can do, but does get the job done. Other thing you can notice is that you're multiplying by h every time, so you can just pull that h in front of the sum basically and do this. Integral, you multiply integral by h. Right? You should get the exact same result.